Yeah.
So do you want to just greet our speaker because it's late night for him? Thank him for joining us this late in the night just to give us teach us some things that he knows so well. Do you want to just greet him before we get started? All of you, please unmute yourself and just say hi. I think a lot of people are probably they joined in and left, is it? So, guys, please unmute yourself and say hi to Peyman.
Hi, Peyman. Hi, Peyman.
Hi, hi. Hi, everyone.
Hi. Hi.
Nice to see you.
Hi.
Hi.
And I should say it's really not very late for me. It's only 8:30, so but it's pretty early for you. So I appreciate you getting up and coming to listen.
Yeah, thankfully the daylight saving has changed, so it's not as bad.
Right. It's not bad at all.
Yeah. Yeah. Cool. So my name is Gaurav. I'm a research scientist with Google Research India, and I would like to thank and welcome Peyman Milanfar, who has gracefully agreed to give this lecture for us. And I have known Peyman ever since I was a grad student. I mean, I have probably started my research career reading his papers, so I have like immense amount of respect for what he has done. And I don't know if you follow him on Twitter. If you don't, I think it's as a mathematical fun Twitter handle to follow as you can ever get. It's accessible. It's not so or esoteric that you can't understand it. I remember like recently I saw a tweet from him. He has written a white one pager on how do you compute EMIs like in your mind without like and which he learned from his father, if I recall right. And it was fascinating to read that one pager. So if you want such tidbits, it's not just vision, but just simple statistical mathematical tidbits, which we encounter every day, but we ignore typically. Go ahead and follow him. It's as much fun as you can get if you are mathematical in your approach and things. So thank you, Peyman, for agreeing to give this lecture. So just to introduce him, Peyman received his undergrad in electrical and mathematics from UC Berkeley, and then went on to do master's and PhD in electrical engineering from MIT. He's a principal scientist at Google Research, where he leads computational imaging team. Before this, he was a professor of electrical engineering at UC Santa Cruz. He was also associate dean for research at the School of Engineering from 2010 to 2012. He founded Motion DSP, which was acquired by Cubic. From 2012 to 2014, he worked with Google X, where he helped develop the imaging pipeline for Google Glass. Most likely, you guys would have heard of this product from Google. His team at Google developed the digital zoom pipeline for the Pixel phones. Those of you who have probably never used Pixel phones, I mean, a lot of camera phones these days they talk about like how many sensors you have and stuff, but if you look at Google Pixel phones, I mean, they do more with less hardware actually. So a lot of magic that you see, especially the night sight. I don't know if you have ever seen that. It's magical. I mean, and probably some of the magic is done by Peyman and his team. So try it out. If you don't have Pixel phone, just go to YouTube or somewhere and check it out. It's amazing. And Peyman is also a distinguished lecturer and fellow of IEEE for contributions to inverse problems and super resolution in imaging. Thank you, Peyman, again. And just a few logistical items before we get started. So this this talk will be recorded. So whatever you say or do here will probably be there forever somewhere. So I hope you're okay with that.
Yes, indeed.
And
yeah.
So yeah, I mean, I meant to say even for others like attendees, not just for you. So the whole session is around 1 hour 30 minutes. First 45 to 50 minutes will be for the talk, followed by discussion. If you have any questions in the middle, and you can please type them down in the chat. You probably would have done it already in the previous sessions, and post that we can take them up one by one. Yeah, I think that's it. And and when you do ask questions later on, please switch on your video so that Peyman gets to know who you are and introduce yourself before asking the question. That will just make it more interactive than just blunt questions. So thank you again for joining this session, and thank you, Peyman. We can get started.
Thank you very much for that really nice introduction and the endorsement of my Twitter account. That's really great. Indeed. So today I'm going to talk to you about computation and photography, which is a subject that I've been working on for many years. The talk will be kind of in two pieces. The first will be more historical, and the second part will be more technical. As I started thinking about how computational photography has evolved, I realized that there's a lot of interesting history. And so a couple of years ago, I kind of dug into the history of computational photography, and I just want to bring that to you because I think it's something that we kind of all take for granted, but we don't really know much about. And so after the first part, I'll give it a little pause. I'll stop. If people want to kind of ask a couple of questions, we can do that, and then I'll continue with the second part. All right, so let's get started. So I think it's pretty clear that the smartphones have changed the world. I don't think I'm really exaggerating here. Pretty much every part of humanity in some way or another has been touched by smartphones. But I want to give you a concrete example here of something that hopefully will drive the point home. Here's a picture that was taken at the Vatican Square in 2005 when Pope Benedict was announced. And I want to draw your attention to the little corner of this picture, and you'll see someone with a flip phone taking a photograph, and there's really just one lonely person doing this. And now let's fast forward to 2013, when the next Pope was announced, Pope Francis, and you can see literally everyone is, they're not really looking at the Pope, they're looking at their screens. And the world has changed and remained this way and continued to evolve ever since. So this was really a striking example for me. And of course, now we're almost 10 years past 2013, so things have changed even more. Now, from a kind of numbers point of view, this chart is actually from 2017, and it shows a striking figure here, which is that at that point, and now it's probably more than 85%, at that point, 85% of all photos taken in the world were with smartphones. That's really quite amazing. And what that means is that basically digital cameras, standalone cameras, are relatively rare. People don't really carry them around anymore because the capabilities of the smartphones have gotten so much better over the years that there's really not much of a need for carrying the second one. And so that's kind of the arc of this talk, is how did this happen and why did it happen? Another bit about numbers. This is, again, a slightly outdated, maybe a year or so old. More than 2 billion photos are shared on social media per day. And of these, over 100 million are selfies. And that's really interesting kind of commentary on the world, right? We like to take pictures of ourselves and share them around with friends and family and so on. Okay, so let me do a little bit of a timeline. The history of photography is very interesting and very rich. Lots of really fascinating stories. I'm not going to go too far back, and most of what I'm going to say is going to be for the last 20 years or so. But there was an old school of photography with these rather large formats that dates back to the 1800s. Then in the 1930s, cameras were built which used analog phone. Many of you may not, obviously, are not old enough to remember those things. In the 1990s, digital cameras were introduced. I'll say more about that. And then really since 2010 is when the research and the computational side of things and mobile devices have really taken over. And so most of my talk will be concentrated, at least the technical part, on the mobile and computational photography part. Okay, so let me say a little bit about analog photography. So analog film dominated, it was introduced in the mid-1930s and dominated for about 50 years. And Kodak was a major player in that. Analog film was largely discontinued around 2005. There's been a small recent resurgence of it, but really it's not much of a factor economically anymore. Digital photography, of course, became what replaced it. And there's an interesting story of kind of how digital photography came to replace analog. Let me take you back. The first digital camera prototype was built around 1975. It looked like this. It's this thing on the left-hand side. It's this behemoth. And what you see is the thing on top in blue is the actual camera. There, underneath it, there's a big computer. And this thing was able to capture an image at 100 by 100 pixels. And it took 20 seconds to shoot a single picture. And the picture was recorded on this cassette. And then if you wanted to play back the photo, you would have to take this cassette out and put it inside this other microcomputer. and then the microcomputer would scan the cassette, and it would display it line by line on this television screen. So it was quite a contraption, but very novel for the time when it was introduced. This was invented inside a lab by a very young engineer called Stephen Sasson. And when he was very excited about this, and he showed it to the Kodak executives, they told them, you know, no one would ever want to look at their pictures on a screen. They told them, this is cool, but you know, it's ridiculous. Nobody's ever going to look at their pictures on a screen. So they sort of dismissed it. But they did. They were smart enough to tell them, you know, let's file a patent. And the patent was filed, and it was granted in 1978. Now, you would think that Sasson was disappointed as a young engineer that they weren't really paying attention to him, but he persisted, and obviously the technology continued. And Steve Sasson, in fact, ended up receiving a National Medal of Technology in 2009 from President Obama for the invention of the first digital camera. So for you young scholars out there, don't give up on your great ideas, even if they seem completely impractical and ridiculous. Someday you may succeed just like Steve Sasson did. Okay, so with the first digital camera prototype, very simultaneously to that, the Polaroid instant cameras were very popular at the same time. This is kind of an interesting thing to think about. Nowadays, we tend to think about our mobile devices as being things that, including the social media attached to them, as being things that are built for instant gratification. And there's somehow this mistaken impression that this is a modern thing. It isn't, right? So the Polaroid camera was built for instant gratification, right? You didn't have to do anything. You simply pressed the button. There was nothing to focus. There was no adjustments to be made. The thing popped out, and you got to watch it develop. It was beautiful, and you got to share it with people right away. So this notion of instant gratification has been always with us from the very beginnings of photography. Okay, so the first commercial digital cameras were introduced in the 1990s, and there were these kind of strange objects in some ways. I mean, they look familiar to you, but let me say a little bit more so you can judge for yourself. This device on the left-hand side was built by Logitech in 1990. It had a few hundred pixels on the side, the camera, black and white, 256 gray levels, 1 meg of internal RAM. And guess what? It cost $1,000 at the time. And we're talking about $1,000 in 1990 dollars. That's a lot of money for 30 years ago. And obviously, it didn't sell very many. These things on the right-hand side look more like the digital SLRs that we have today. And in fact, they were the predecessors. These things cost as much as $20,000, and they sold very few units. But one thing I want to draw your attention to, which is very interesting, is that solid-state memory at the time was neither cheap nor small. And so if you owned a camera like this Nikon here on the left-hand side, and you wanted to take a bunch of shots, let's say a few dozen shots with it, you couldn't store them all on the camera itself. So you had to carry this huge thing on your shoulder, which was a tethered external hard drive. So imagine you had the camera and you had this big thing on your shoulder that would store the images in it. It was quite bizarre experience to go photographing with that out in the wild. Okay, moving on. CMOS, which is the dominant technology for photography now, was invented in 1993. And you would think that it would immediately revolutionize the industry, but it didn't. It would take at least another 10 years before the manufacturing of these devices would be fast enough and convenient enough, and the technology would be advanced enough to make it into affordable mobile cameras. They were far cheaper to make. They still are power efficient, but they're noisier. They have a rolling shutter readout, but they did end up replacing the CCDs. So moving on, digital SLRs and compacts were introduced in the early 2000s, and this is what they look like. So these cameras on the left-hand side are very familiar to me. My own kids were born on either side of the year 2000. So most of the pictures I have of my kids when they were little are on these Canon PowerShots. I had a couple of them over the years. They were pretty good cameras for 1.5 megapixel resolution. They cost about $500. And the serious kind of professional quality DSLRs, digital SLRs, or things like on the right-hand side here, and they cost about $3,000 to $5,000. Okay, so remember these two numbers. For the point and shoot, about $500, and for the more professional quality, $3,000 to $5,000. Now let's take this, and these were CCD based, and let's speed forward to today and look at the equivalent cameras that are on the market today. The Sony RX100 is a fantastic camera. It takes 20 megapixel shots. It has an amazing lens, and it's just a fabulous camera to have in your pocket. And it still costs $500. And this camera, the Nikon D810 on the right-hand side, 36 megapixels, and guess what? It still costs $3,000 to $5,000. So if I just go back and forth and look at these two things, what's happened is that the cameras have become fantastically better, but in relation to the quality and the value that they brought to users, their cost has stayed relatively the same. And this is a really amazing thing that has been enabled by both economies of scale, because many, many more people are willing to buy these devices, but also by the advancements in technology and the ability to make these devices much more quickly, much more conveniently, and more cheaply. Okay, so this is kind of, you have to think so many things have to happen in order for a device to get better and better and better, and yet the price remain more or less the same over the course of 30 years. That's really quite amazing. Okay, so now let's move on to mobile photography. Okay, so let me go back a little bit to talk about mobile photography. So in around 1997, a patent was filed, and the title of this patent was Electronic Camera with Programmable Transmission Capability. Now, if you look at the pictures that were included in this patent, you will see this thing here. What does that look like? It looks very much like the early prototype of a mobile camera, of a mobile phone, doesn't it? With the small screen and the keypads and all that stuff. Maybe you would be surprised to know that this patent was in fact filed by none other than Kodak. I was amazed to find that out. What's interesting is that Kodak actually did not continue to invest in this area, and they ended up sort of, in some ways, not capitalizing on the intellectual property and on the inventions that they had very early on. And the reason they didn't is because in some ways they were fearful. At the time, you have to remember, they dominated the analog photography market. And they were somewhat fearful, the story goes, that by investing in digital technology, they would be eating into their own core business. They would sort of be self-sacrificing their own core business. And so they held back. And because they held back, the rest of the world sort of moved on and capitalized on this. And of course, after a few years, the patent expires and everybody else gets to jump on board and do the same thing. Okay, so that opportunity for realizing the first commercial camera phone, and this looks very much like the picture that was in the patent, you remember, was in fact that first commercial camera phone was introduced in Japan. It was built by Sharp. It was sold in the year 2000. This is what it looked like. And these are the pictures that it would take, this picture on the left-hand side. The camera really wasn't much to write home about because the equivalent devices that cost $500 were these point-and-shoot cameras that provided you with much better pictures. So people didn't really buy these devices because of the cameras. So it wasn't entirely a huge success immediately when it came out. But it took a few years, 2 or 3 years, for the rest of the world to kind of understand the value of these devices. And the first camera flip phone was introduced in the US, at least in 2002. And the year after that, the forward-facing camera was for the first time installed in these devices. At the time, these forward-facing cameras were called video call cameras. They weren't called selfie cameras. And the word selfie hadn't been invented yet. Okay, so that was kind of interesting. And I remember using these for video calls. It didn't really work very well. But anyway, that was the origin of the technology. All right, so the really fundamental big event that happened was in 2007 with the introduction of the iPhone. And it is generally assumed that the introduction of the iPhone somehow absolutely revolutionized mobile photography right away, but that wasn't really the case. If you go back and look at the details of how that device was rolled out, Apple did in fact reinvent the phone, but not so much the camera. the invention at the time was mostly about the display and the user interface. There was no other device available at the time where basically the entire phone was the display, right? And that was a huge innovation. All of these other competing devices had physical keyboards, and the iPhone got rid of the physical keyboard, and that was a fundamental change. And Steve Jobs gave a now historic keynote address introducing the iPhone to the world. It was about 45 minutes long, and literally he said one sentence about the camera on the iPhone. He said, on the back, the biggest thing of note is that we've got a 2-megapixel camera built in. That's it. That's all he said. Why? Because at the time, the competition was these compact cameras that did far better at photography. So there was really nothing fundamental to brag about with respect to the camera. They just threw it in there because they could. Okay, so what happened that really made mobile photography so popular? There are two events that kind of simultaneously conspired to make mobile photography really convenient and useful and widely adopted. And these two things were the introduction of high-resolution displays and 4G networks. So let me say a little bit about each one of these things. In particular, the 300 dpi display basically made it so that you could consume the camera photos on your own screen, and because of the 4G network, it was fast enough that you could share it with other people. And that made it so that you enjoyed the pictures on your device, and your friends could enjoy the picture on their device. And it was fast enough to do that. And so people basically naturally adopted this. So this is kind of what the displays looked like. And in terms of the network speed, if you wanted to transmit a 2-megapixel image, which is still to this day the average size of an image that is transmitted through the web, especially on social media, in 2000, it would take about 30 seconds. In 2010, it would take about half a second. So that was really a fundamental shift in terms of convenience of sharing. Okay, so that's kind of the rough historical setup that I wanted to give you. And this brought us to just about 2010, when computational photography became the thing, and there was a lot of research in the academic community. And eventually, slowly, these things began to make themselves available inside consumer devices. So I'm happy to stop now and take a couple of questions or comments, take a breather, and then I'll continue with the next part. So if there's any if somebody has a couple questions, I'm happy to take them now. Okay.
Do you have any comments on? Sorry.
Yeah.
Yeah. Do you have any comments on Project Ara, like modular camera and stuff?
No, I don't have any comments on that just now. So let me go through the technical part. I think your question is more on the technical side of things. So maybe we can talk about that a little bit later.
Thank you.
Mm-hmm. Okay, so this era, sort of, if you like, the last 10 or so years, is characterized by this quote: "The best camera is the one that's with you." And the idea here is that you have a camera that is on your phone, and you don't need to carry a second camera with you. Okay, so let me give you a little bit of recent history at Google. So this kind of reflects my own experience and my own interaction with these devices. In 2012, I joined Google as a visiting scientist. I was recruited to help with the pipeline for the Google Glass device. There we developed the first burst processing pipeline, and I'll say more about that in just a minute. The pipeline that was developed for Glass was eventually transitioned to the Nexus line of phones. And then it evolved to the pipeline that currently sits inside the Pixel line of phones, starting with Pixel 1, 2, 3, 4, and now Pixel 5, and so on. Let me motivate kind of how we think about this problem. The idea is that we want to have one camera in our pocket, right? So one has to ask this fundamental question: can this device on the left-hand side, which is a mobile phone, possibly just one or two cameras, can it compete with this device on the right-hand side? There are obviously physical limitations. And so, for instance, if you look at just the aperture, this mobile device on the left-hand side captures 300 times less light, right? So there's really not a whole lot you can do about that, right? The physical aperture is what it is. So we have to overcome this, this shortcoming with additional processing or some other clever technology, and that's exactly what we're going to try to do. It's not just the amount of light that comes into the camera, it's also the size of the sensors that capture the light. So for a device like that Pixel that you see on the right-hand side, I think that one is a Pixel 3, you're talking about something like a 5.5, 6 millimeter size sensor, and obviously the thing on the right-hand side, 35 millimeter, right? So there's an enormous difference in terms of the area and the size of the pixels. And if the size of the pixels are much larger, you can have more area to capture the photons. So the solution has been, in some way or another, not just for Pixel devices, but for devices across the industry, to compete with hardware. And the following interesting thing has happened. You know, you've got devices with 1 camera, with 2 cameras, 3 cameras, 4 cameras, 5 cameras. And I'm not exaggerating here. These devices are actually on the market. You can buy them. But if you look under the hood, most of the improvements, especially on our devices, on the Pixel devices, are due to the software, are due to the clever things that you can do with software. So let's think about, like, what is it that you want out of a camera, especially a small form factor camera like these, you know, these very thin, small devices. You want to get more light. I just tried to motivate that. You want to get more dynamic range. You want to be able to capture things that are really bright and really kind of in the dark, like in the shadows. And you want better resolution. You know, just the number of pixels we have available to you on mobile devices is smaller. So one thing you can do to capture more light is to use a flash. If you ever use the flash, you'll know that it's kind of an unpleasant experience. It makes your subjects kind of look a little bit odd. The lighting looks a little bit odd, and its range is very limited, right? So if you can't illuminate the entire scene, you can illuminate just a few things that are relatively close to the camera. You can do things like use longer exposures or bracketed exposures. Now, if you just use longer exposure to get more light into the camera, you're going to get blur, right? So things just move, and you're going to get smearing across the image. You can also use bracketed exposure. We do that, and many people do that. That's also rather complicated. If you just take 2 pictures that are exposed differently, you tend to get a lot of artifacts with ghosting and so on and so forth. So what we settled on, and what I think kind of a lot of the industry has settled on, is to capture a burst of images. And the way this works is we capture a sequence of images rather quickly, and we then take this burst of images and merge the images together to get a single image out. Now, the way this works from a technical standpoint is that as soon as you turn the camera on, the camera is shooting, and the photos are getting stored into a ring buffer. So there's a constant stream of photos being fed into a ring buffer. And this all is happening before you ever press the capture button. And then as soon as you press a capture button, a sequence of frames are pulled out from that frame buffer and fed into memory, and then we are able to process them, as I will explain shortly. Okay, so this has now become the kind of workhorse of mobile computational imaging, has become this burst photography. The very first step in this process is exposure control. So as you turn the camera on, the camera is observing the scene, looking at and measuring the average brightness in the scene, looking at the brightest thing in the scene and the darkest thing in the scene, looking at whether things are moving in the scene or if they're stationary. And all of these things are fed into an algorithm that decides how you're going to expose the scene in terms of how many shots you're going to capture, how long each shot is going to be, and what the total exposure time is going to be. And the total exposure time here is the sum of all the exposures and the times between the exposures that you have. Okay, so that in itself, that exposure control, is a fairly sophisticated step that decides how the burst is captured. And how long the burst is going to be, it depends. It may be as few as 3 or 4 frames in good light, or it may be as long as 10 or 15 frames in poorer light. So the next step is alignment. These images, in order for us to produce a single frame, they have to be aligned very, very accurately with one another. And so here, for those of you who work in computer vision, you have to do optical flow estimation. And this has to be done very reliably. You have to remember that the scene is almost never stationary. So there are objects in the scene that are constantly moving. There will be cars moving, people moving, clouds in the sky, you name it. And there's also the camera that's in your hand is also moving because your hand is never perfectly stationary. So that's one thing that has to happen. Once you've done the alignment, more or less, as accurately as you can, then the next step is merge. You have to basically reduce all of these frames into a single frame, and that is done by some kind of weighted averaging of all of the frames. Now imagine if the frames were not moving with respect to one another at all, then all you would have to do is simply average all the frames together. But that is not possible because everything is constantly moving. And so here you are at the risk of getting alignment failures. You may be getting occlusions because objects over the course of time when the capture is happening may end up hiding behind one another. The car may go behind another car, or a person might walk behind a sign, etc., etc. And then the final step is once you've done the merge, you have to do some single frame enhancements. And these include things like noise reduction, denoising, sharpening, contrast enhancement, and dynamic range stretching or compression. And so these are sort of the 3 major areas of technology that you have to develop in order to do this. Now, I want to pause here and point out that all of this happens in around 1 second. Okay, so we're capturing the frames, aligning them, merging them, and enhancing them. And once you've hit that capture button, to give you a sense of how long 1 second is, the time it takes roughly for you to press the button and then go to the gallery to look at the image, that is how much time we have to finish everything. Okay? So one of the major challenges is to do all of this fairly sophisticated work and do it on a mobile device. And of course, to every mobile engineer's chagrin, people love to do things like hold the device up and tap, 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 right? Like take lots of pictures all at once. And so that's one of the situations where we're like, okay, we have to really be good engineers because people are not just going to be like, boom, here's one picture. They're going to take 6 or 7 pictures all at the same time. Okay. All right, so let me go back a little bit and give you a little more technical flavor for what a classical camera image processing pipeline looked like before this burst processing pipeline came on the scene. So a typical camera, here's a CMOS camera on a chip, kind of camera module. The sensor typically has a color filter sitting on it. And what happens is that this color filter is actually not allowing the pixel to see every color. It is only, every pixel is measuring only one color, right? So a typical pixel value is red, green, and blue. But here we only measure one pixel at a time. We can't afford to measure all 3 at the same time. And so there are various steps that are taken, and you can ignore the gain control and all this other stuff, white balance, but demosaic is one of those key steps which means that all of these values are converted and approximated so that you can get full color values for every pixel. And the rest of these steps I will explain in broader context in a moment. And so what I described earlier as the merge step in the burst processing pipeline, the demosaic is in some sense for single frame pipelines is like that merge step, because you're trying to merge information from nearby colors to reconstruct the color that is missing at every pixel. Okay, and then the rest of these steps that I mentioned, tone reproduction, color space transform, noise reduction, and so on, these are sort of like the enhancement step that I mentioned earlier. Okay, so let's talk a little bit about the technical side of demosaic. So when you buy a phone and on the advertisement, it says that this has a 12 megapixel camera on it, we are maybe in some benign sense lying to you a little bit. The reason why is that 12 megapixel sensor doesn't mean you have 12 million RGB pixels available. A lot of the color values are missing. And so what we do is interpolation. So from all the red values, we might interpolate the red value in between, green, blue, same thing. And so if you think about this, at the end of the day, 2/3 of your picture is made up, right? At every pixel, only one color is measured. Now, you know, if you went out and made this point to the average consumer, they might want a discount on the camera, I would think, right? So I always find that interesting. So what is the relationship of this to the burst processing pipeline that we developed? Well, we wanted to see if there's a way to do demosaicing, or if there's a way to replace the demosaicing step. It's one of the kind of Achilles heel of the process. It's one of the steps in that pipeline that is the weakest in terms of reproduction of a good image. So here's an example of what a mosaicked frame looks like. This is just illustrating this little piece of the image that is indicated here in red. So if I were to take this image and I were to do this interpolation that I described to you with a state-of-the-art demosaicing method, I will get this image in the middle. Now, this is not that great, right? A lot of details are missing. You can't read the text on the signs, et cetera, et cetera. So what we want to do is to replace this demosaicing from one frame with demosaicing using multiple frames. And if you do that, you get this image on the right-hand side. Now, you might say, well, this is not perfect either, and you would be absolutely right. But it is actually far better than this thing in the middle, and you will see the results of how this propagates through the rest of the pipeline in the slides to come. Okay, so how do we do this? How do we use multiple frames to replace the demosaicing with something more sophisticated? Well, one way to do it, one way to think about it, kind of a cartoonish way of thinking about it, is something called pixel shifting. So imagine you have this image, and these are the color pixel values that are available to you. Now imagine that somehow magically you could perfectly shift your sensor 1 pixel, exactly 1 pixel to the right. If you did that, in addition to the pixels that you've just captured, in your second shot, you would capture a bunch more colors, right? And so you would kind of span some of these missing pixels, and you would get some of these other colors. Now assume that you could do this again and shift the sensor 1 pixel down exactly. Now you would get some more colors. And now say you could shift the pixel sensor down 1 pixel and to the right exactly 1 pixel. Now you would have spanned all the colors that you're missing. Okay? So hey, success. If I can somehow move the sensor exactly left, down, or right, down, right and down, I get all the color values that are missing. But it's not easy to do. It turns out, obviously, we weren't the first ones to come up with this idea. This has been done in some of these more expensive cameras. It's called the pixel shift mode. Cameras that do this cost upwards of several $1,000s. They, in fact, do exactly what I said. They physically move the sensor that's sitting behind the lens. They move it around, and they capture multiple pixels. However, when they do this, the camera has to be sitting on a tripod, perfectly still, and there has to be nothing in the scene that is moving, right? So it only works for a perfectly static scene. But life is not so simple, right? And what we wanted to do was to do something like this, but do it in the wild for a device that is handheld. If you do it in the wild, these pixels are not going to land in a very orderly way in places that you want. They're going to land in kind of random fashion. And so what you're going to get in this larger grid of pixels is you're going to get this possibly fairly wild distribution of the different colors. And so in the end of the day, you're going to have a multidimensional non-uniform interpolation problem if you want to get back from these pixels that are incomplete to a full red, green, blue image like this. Let me give you an example of what the sequence of images look like, this burst of images looks like in a scene. We took this just outside of our offices a couple of years ago. And if you look, this is a burst that lasted, I don't know what it was, probably, you know, maybe a third of a second or something like that, maybe less than that, quite a bit less than that probably. And you can see there's cars moving in the background in this area, but there's also a relatively mild movement of the entire scene, and that's due to the camera motion, which is in your hands. Now here, of course, I took this picture. I tried my very best to keep the camera completely stationary, but as you can see, it's rather impossible. Okay, so now let me show you a little bit of detail. That's the area that I'm looking at. This is what that area looks like. Okay, it moves. Now, what I'm going to show you next is this sequence of images aligned with one another with respect to one of the frames as the reference. And what that's going to look like is this. Okay. Now, you would imagine that since I've aligned everything very, very accurately here, nothing should be moving anymore, right? But there's still things moving. And there's two reasons why things are moving. One is something called aliasing. Aliasing happens when you have a signal or an image that has been sampled, or the number of pixels is sufficiently low, so it hasn't been sampled finely enough, so that some of the higher frequencies get folded into lower frequencies. This is the Nyquist rate, basically. So the Nyquist rate has been violated here, and that typically happens in mobile phones. The number of pixels that you have is not sufficiently high that it would capture all the high frequencies in the scene. So that's one thing. And the second thing is, it turns out no matter how hard you try, the camera is never perfectly stationary in your hands. And the big motion that you saw there isn't even the only thing. There are actually very, very slight motions that occur in the scene due to your hand as well. And so this thing, it turns out, is due to something called a natural physiological tremor. This has been studied for many, many years, since it was identified in 1886. It's been written about in neurology journals for many, many years. It's been studied in biomedical engineering for many years. This effect is available. This effect is something they have to deal with in microsurgery, when the surgeons are operating at very, very fine scale. Their hands are moving so little that it's imperceptible, but it can make a very big difference when you're doing microvascular surgery. What I'm showing you here on the right-hand side are actual measurements of horizontal and vertical displacement, angular displacement, on a real camera from hundreds of bursts. And so what you see is that basically the camera is moving ever so slightly, kind of vibrating in your hand ever so slightly without you really noticing. And so this effect seems like it's a bad thing, right? Like I said, in biomedical engineering and in surgery and so on, they try to fix this. We actually take advantage of it because we can't perfectly move the sensor around to get those subpixel color values. We actually use this physiological tremor to do the same. Now you might ask, okay, that's fantastic, very cool, but what if I put my camera on a tripod? The camera is not moving anymore, so how are you going to do your fancy processing if the camera isn't moving? Well, we did something that actually simulates this hand tremor, and we did it with something that's called the optical image stabilizer. The optical image stabilizer actually physically actuates the optics of the camera to try to stabilize the image. But when the image is actually perfectly stable, we can also control the optical image stabilizer to move the image on the sensor. And so we turned it on its head and used it for this purpose. And you can see this actually if you own a Pixel phone. Take it, put it against a window, and then zoom in all the way so that you can see the finest motion, and then you'll see things like this happening. So you see it's a very slight wiggling behavior that you see. Okay, so with this, our processing can use the combination of this very, very small motion plus the aliasing that I mentioned to you to obtain higher quality images. And this basically is the fundamental idea behind doing super resolution. So the sequence of images that we captured here on the left-hand side are turned into an image that is on the right-hand side. This is from the lobby of our old building, actually. And you see there's a lot of fine textures on this couch, and they don't look very good if you don't do this processing. It turns out that there's something similar to this happens in the visual system. I apologize for the slightly creepy moving eye in the picture here, but this is real. Your eye is constantly moving. Again, this is not something that you're generally noticing at all, but it is constantly moving, and this miniature eye movement, it turns out, it has been studied, and it turns out to enhance fine spatial detail. This is one of the reasons, apparently, why you're able to see as well as you do. The quality and the detail with which you are able to see is not explained by the number of rods and cones that are in your visual system. Of course, you have a tremendously powerful computer in the form of your brain as well that does a lot of interpretation, so that's also extremely important. Okay, so let's talk a little bit more technical here. You have, as I said, with this random movement, you may get widely different distribution of colors that you are able to capture in different parts of the image. In some places, you're going to get very dense coverage. In other parts, you're going to get very sparse coverage. So what you require here is the ability to be able to do non-uniform interpolation. And this is where a little bit of mathematics, a little bit of non-parametric statistics and related techniques have come in to help us a great deal. The way we merge these samples together is something called kernel regression. The way kernel regression works is that every sample basically gets a bump associated with it. And the shape and the size of this bump, you can see like this one is kind of long and narrow, and this one is shorter and wider. So the shape and size of these bumps are adapted to the density of the data and the value of the data. From these, we add the contribution of each pixel according to these bumps. These are called kernel functions. And from this, we get a continuous interpolation of the signal. Now, once you have a continuous interpolation of the signal, you can resample that continuous interpolation to any grid you like. And that's exactly what we do. So here's an example. We took a burst of images of this scene. In this particular case, it happened to be a stationary scene. If you take all of these images and merge them onto the native grid where the RGB pixels were, you get this image. If you merge onto a grid that is denser, like 1.5 times denser, you get this image. And you can merge it onto a grid that's twice as dense, and you get this image. At this point, you may be tempted to say, well, how about if I just keep going? How about if I merge onto a grid that's 10 times more dense? Will I just get, I see the atoms? No, you won't. The nature puts a stop to this, and this how far you can go really depends on the trade-off between the size of the pixel, the optics of the lens, the spot size of the lens, the amount of noise that you have, and how much motion you have, and many, many other factors. But for a typical mobile sensor, you can go as far as 2x. So you can get 2x super resolved images from a native resolution camera. And so that means that with a fixed lens and a fixed sensor, you can get much better quality than you would expect just from the hardware with some more clever processing. What do these kernels look like in 2 dimensions? And you can see here's an example of them. So along the edge, you remember these kernels that I showed you that have this kind of Gaussian shape. Now in 2D, they're going to have correspondingly kind of elliptical cross sections. And so when they're landing around an edge, the elliptical shape kind of stretches itself so that you're aligned with the edge so that you don't blur across the edge. This is an illustration of that. So the way this works from a practical point of view is we have a parallel process that aligns the frames to a key frame that we call the base frame, estimates the contribution of that frame, samples this continuous interpolation, and puts everything into an accumulation grid and produces the merged image. So here's a few examples of this. So if you look at this picture of the Golden Gate Bridge, this on the left-hand side is what we would have gotten, and this thing on the right-hand side is what we get from this particular merge process. Show you a few more examples. This here, you can really see the effect of recovering higher frequencies. So the roof tiles of this cabin in the distance are kind of mixed together or just wrong in the top picture, which is the old method. And in the new method, you can see the tiles are very well resolved, and you can see really details that were not visible there before. I'll be happy to share all these slides with you as well, so you can examine all these things by yourself later on. So very interestingly for us, this software, when we first released it on the Pixel 3, it was evaluated independently outside of Google by many places. One of them was DP Review, which is a photography magazine, and they compared our device and our software, the quality of our images, to many things, including some point-and-shoot cameras and other more sophisticated cameras called Micro Four Thirds sensors. And what they said was the Pixel 3 is the first smartphone camera to rival cameras with Micro Four Thirds sensors. Micro Four Thirds sensor cameras are standalone cameras, right? So with a mobile device, we can now take images that are the same or better resolution than standalone cameras. So this is kind of where we started. This was, can we get this far? It turns out we're nowhere near this thing on the right-hand side, but we did manage to switch the order between these two, right? So we made one step closer, and we're continuing to work. But at some point, you can imagine physics is going to stop us from going all the way to being able to meet the quality of a 35mm camera. And part of that is because we are never going to have a mobile device like this be this thick, right? And that is fundamentally an advantage that a standalone camera has. It has a long lens, it has a body, and there's a very big distance between the focal length of the optics and the sensor, and so there's a lot that they can do there. Fundamentally, the big difference between mobile devices and standalone cameras is mobile devices have less sophisticated optics and more sophisticated processing, and exactly the opposite is true for standalone cameras. They have very sophisticated optics and almost no computing power inside the camera. So they're kind of at opposite ends of the spectrum here. So this particular work was written up and published at SIGGRAPH 2019. The paper is available online. You're more than welcome to look at it and get in touch with me if you have any questions. So I want to take you in the last few minutes through some use cases of this. So Gaurav mentioned night sight and super res zoom, so I want to say a little bit about it. So night sight, of course, you've seen, produces beautiful pictures of the night sky. What we used this merge process for here wasn't so much to get super resolution. It turns out it's very difficult to get super resolution when the scene is very dark. But here, because the scene that you're imaging is moving a lot over the course of several minutes, you need a very stable merge process. And so for this, we adopted the merge process in the initial launch of the night sight to be the same as what we do for the super res zoom process. In the zoom use case, again, as I said, this merge process is giving us additional resolution. But if you're zooming onto a part of the image that's bigger than, let's say, 2x, you still need to crop and blow it up, right? And so it turns out that this cropping and blowing up requires another upscaling process. And this upscaling process is something that we developed using a method called Razor. This is a filter learning process. This is a machine learning algorithm, very lightweight one, that basically collects values from low resolution and high resolution images and solves a loss function, and we learn filters. And we don't learn just a single filter, we learn a bank of filters, and then for each pixel we decide which of those filters we're going to use. Well, I'm going to skip over this. But anyway, so here's an example of what these filters look like. So the way this upscaling method works on the output of the initial merge process is that every pixel, we go and we look at the local statistics of that pixel. We basically measure features of the neighborhood of that pixel. And that gives us an indicator of which of these filters we should use to upscale that part of the image. And then all of those pieces are stitched together to produce a final image. So here's kind of an end-to-end result. Here's the picture with no zoom. Here's the 2x zoom. And I want to show you a little detail of what that 2x zoom looks like. This is if you just did standard digital zoom. This is if you did single frame super resolution only. And this is if you did multi-frame super resolution. Okay? And so this is what we ended up launching. the combination of multi-frame and single frame. And when it was launched, it was considered, and it still is to some extent, the best hybrid optical digital zoom on the market. And you can see the quality differences from just 2 years, from 2017 to 2019, that we were able to realize. In the last few minutes, I want to say a few words about other challenges in computational imaging. Curation is one of them. As I said, in the old days, a roll of film with 12 exposures was expensive, right? So you would take your time and you would set up your shot very carefully, and you would think about whether you were going to press that button or not. Then film got a little bit cheaper, so you were a little less careful. And now you can get thousands of shots at almost no cost, right? You've already paid for the phone, so you might as well take as many shots. So the problem has become curation. How do you search over these many, many thousands of images that you might take every week to find the really good ones so you can share them with somebody? And so here, what we did is we developed a neural network. We call it the neural image assessment. This has become pretty popular now in the literature. And what we did is we got a crowd compute setup to evaluate images and score every image on a range of 1 to 10 for both aesthetics and for technical quality, things like noisiness and blur and so on and so forth. And then we train the network so that now you can feed the network an image, and this is just the details of the network. You can feed the network an image, and it will give you a score between 1 and 10 in terms of its quality. So here are 10 pictures of the Eiffel Tower, and our method has been able to rank them in terms of aesthetic quality. This is purely aesthetic. Now, of course, this is not an individual choice, right? So it may be that this picture with this young woman in it, it may be of particular emotional significance to the person who took it. And they may not care that this one is a better photograph, right? So these are just aggregate scores. It's important to keep that in mind. And you can do the same thing for technical quality. These are all images of the same person, but you can see that the one where the person is well exposed, focused, etc., is scored much higher than when it's blurry and things are moving around and so on. And so with that, I'm going to stop here and thank you for getting up so early in the morning to listen to me. Thanks again.
Thank you, Peyman. This was fascinating. I mean, it's really exciting. I hope all the attendees liked the talk and learned a few things, how the camera phones work. I mean, all the magic that happens in a split second before you see the picture. I think we can potentially take a 2-3 minute bio break before we come back for the discussion. Is that all right with all of you? Cool. So let's come back. I mean, yeah, so we don't have to disconnect, but just if you want to take a bio break or something, then just come back after a couple of minutes.
I'm fine to continue, if you like.
Okay. So whoever wants to just continue, we can then continue. Yeah, we are already a bit late. So I see there are a few questions in the chat. Meenakshi, do you want to ask it yourself, or do you want me to? Yeah, Meenakshi.
Yeah, hi. Hello. Hi. Hello, nice. Thank you for such an interesting talk. So I have 2 questions. The first question is, you mentioned about, every alignment is being done with respect to a base frame. So how do you select the base frame from the burst? That's the first question. And the second question is regarding the last part of your talk, where you showed that a neural network is basically evaluating, giving kind of aesthetic and technical score to images, right? Photographs. So how do you quantify that aesthetic and the technical part of it, a part of photograph?
Right. Yeah. Both excellent questions. So for your first question, how do we choose the base frame? There are many different criteria you can apply. The main one that seems to make the most difference in terms of the outcome, the final quality, is to pick the base frame as one that is least blurry. And that, so imagine in a burst of 10 frames, there's some likelihood that one of them will be more blurry than the other ones, or one of them will be most blurry. You don't want to pick that one, because then you're going to be merging out. So you basically want to pick the highest quality single frame to be your burst, to be your base frame. So that's for your first question. As for your second questions, how do we quantify it? This is really the basis of the whole idea. The notion is, for aesthetics, here's what we did. The data that we relied on were from photography competitions. So effectively, what we looked at was people who participated in these photography competitions. They were sort of either photography enthusiasts or sort of semi-professional photographers. Everybody entered their own photographs into the competition, and then there was a round-robin rating of the photographs by all the other participants. So at the end of the process, every photograph had many, many ratings by many, many other photographers attached to it. So what you could do is you could think about all of these ratings defining a kind of distribution of scores, a kind of histogram of scores. How many people voted for this photo as a 1? How many people voted it as a 10? And everything in between. And so that information became the basis for the training of the neural network. So that was kind of our training data. Is there a ground truth in this case? Of course not. There's no ground truth, right? So the ground truth is every person's opinion of what is important aesthetically to them in that sense. Now, for the case of image quality from a technical standpoint, that's a little bit different story. There you can imagine objectively having, being able to measure the difference between an image that's not noisy and the image that's a little bit noisy and an image that's very noisy. But even there you can do crowd compute kinds of experiments where you provide images of different quality, just technical quality, different amounts of blur, noise, and so on to folks, and have them do the same thing, basically rate the images visually for quality. That's not the same thing as just saying, the standard deviation of the noise is this amount or that amount. So that's what we did. Again, we trained it. So at the end of the day, the scores that we rely on are kind of along multiple axes. Aesthetics is one of them, and technical quality is another.
Can I just add one more point? Actually, this discussion show you, so you are keeping an expert in the loop, right? When we are basically evaluating the quality of the image. So yesterday we were having a discussion on how do you evaluate dance or music if a model is basically generating something like that. So how do you define the quality of it? So I guess there also we were having this discussion like maybe we should keep an expert in the loop or how. But this gives a very nice groundwork for maybe you can take something from there. Thank you.
Yeah, no, I agree. Keeping a person in the loop is exceedingly important in all of these applications. For example, all the work that I described to you in the camera, we never release a version of the software without having experts evaluate the image quality. We never rely on things like our neural network to decide, okay, this is the version of the software we're going to install. This is simply an assistant, if you like. It's to reduce the amount of work that the expert has to do to get to the right decision, as opposed to replacing the expert.
Thank you.
Thanks, Meenakshi. Afroz Fatima, do you want to ask your question?
Yeah, thanks, Gaurav. Thank you for the wonderful talk, Peyman. I just had one question related to the technological front. As I've seen that you've discussed your presentation regarding in the current scenario of a CMOS technology. So I just wanted to understand whether the image quality would differ if you consider certain technologies such as non-volatile memory devices. Considering in picture, and how does this impact to your image or image quality or the video quality which you are considering? So this is actually related to post CMOS era. My question is related to post CMOS era.
Yeah, it's a little bit difficult to kind of project forward, but what I can say is the following. The trend has obviously been, whether you're thinking about CMOS or other technologies, the trend has been to go towards smaller and smaller pixels. And the reason why this has been the case is partly related to being able to advertise that you have a sensor that has more pixels in it. That's attractive in some ways from a marketing standpoint to users and to companies. But also because by reducing the number of reducing the size of the pixels, there may be other things that you can do by creatively combining the pixels together. For example, there are many sensors out there now where there are micro lenses on top of the pixels that point in slightly different directions. So from a single pixel, you can get 2 measurements of the scene at a very tiny baseline, and from that you can build rough estimates of the depth of the scene. So all of these trends towards having smaller and smaller pixels, the effect that they've had is they've increased the baseline noise that you experience in your images. So the net effect has been that the importance of processing and software has steadily increased over time, and I anticipate that will continue even with the next generation of sensors. They will make software and good software and strong technical contributions in terms of algorithms even more important over time.
Thank you.
Cool. Gotham, do you want to ask your question?
Yes, thank you. So, sir, I would like to know how the exposure control works on videos. Is it in the same way as in images, like you iterate multiple times?
Yeah, I mean, the very basic algorithmic way that exposure control works in video is very similar to the way it works in images. However, there is one fundamental difference, and that is we cannot and we do not change the exposure level on a frame-by-frame basis when we're capturing video. And the reason why we don't do that, well, it's partly because the scene maybe isn't changing that much, but also because you can imagine if you're shooting video at, let's say, 24 or 30 frames per second, you don't want to change the exposure at every frame because you're going to get this flickering effect, right? So you want to maintain some level of continuity. So the basic algorithm is the same, but there's temporal smoothness built into that algorithm so that we don't introduce too much variation.
Yes, thank you. Thank you.
Usman, yes? Do you want to ask a question? Oh, you want me to do it? Okay. Okay, I'll try to just read the question. It says, for DICOM medical images, there are huge sizes, about more than 140 GB. So it gets difficult to download them and work on them when we work on Kaggle or Google Colab. So usually we convert them to JPEG or PNG, but the resolution degrades, and we are not able to detect the small objects in non-use. Any suggestions on that?
Yeah, that's an interesting challenge. I'm not sure I have any particular suggestions since the use case is so very specific. But I would say, I guess I don't know what are the compression mechanisms that are used here. It may be that some, if it isn't already, some particular forms of more sophisticated compression may be useful here. There are other standards that are applied to medical images that are not just standard JPEG or PNG. There are other forms of lossless compression that are applied, so that may be useful here. Something that we do to avoid kind of having to store or download really large images is that, you've seen we have some fairly sophisticated upscaling methodology. So one thing you can do is instead of storing or transmitting the original image, you can downscale the image, store it or transmit it, and then when you need it, you upscale it. This works fine for images at various qualities and in many different situations, but I would actually strongly advise against it for medical images because for the very reason that you mentioned here, there may be subtle differences that are diagnostically relevant that you don't want to lose. So I wouldn't do what I just suggested.
Let's move on to the next one. Wasim Shai. Wasim, do you want to ask your question?
Yeah. Hi, Peyman. Thanks for your wonderful insights. Actually, I had a doubt like what would be the role of emerging non-volatile memory devices in image processing devices? And also a second one, follow-up question of, as you have rightly mentioned, there is a limitation for mobile phone cameras in terms of gathering number of photons, but also the mobile devices are also limited in their power and computational resources. As we can see, there are, as you have also said by answering one of the questions, like the software algorithms are getting more and more powerful. So how do you see the next few years of these image processing techniques of software, and what type of hardware is required to handle such type of load? Any thoughts on that? Thank you.
So on your first question, I don't really know a whole lot about non-volatile memory like RRAM, so I'm going to kind of pass on that one. On the second question, that's a great question. One thing that we realized over the years is that a lot of what we have done, at least a lot of what we did originally as we began to bring kind of state-of-the-art technology from just being nice publications and so on into production, was that we ended up with technology that required fairly heavy compute. And we are fortunate that a lot of the devices, both the Pixel devices and the iPhones and so on and so forth, have fairly heavy compute. But I personally think that the next frontier for our technology is to bring these really advanced techniques to devices that don't have as much compute. And I think if you actually, you're probably hinting at this. If you just count the number of devices that are available, mobile devices that are available in the world, probably the overwhelming majority are not ones that have, the most advanced, latest compute in them. And so the question for us is, if we want to have impact with these technologies on a much larger scale, we need to understand and we need to be more clever about how to embed our technology into devices that are maybe not as heavy on the compute side. So this is something we're actively thinking about. We're trying to be more conscious of this. So one of the things that I hinted at was to build much lighter, for example, in terms of neural networks, build much lighter networks that can do the job of much heavier ones. This is sort of the principle of Occam's razor that you may be familiar with. Don't do something that you can do with a lighter tool with a heavier tool just because you have it available to you. So I think this is really great, and it actually spurs a lot of very interesting technical questions. The idea of doing anything under constraint is something that spurs creativity. And I think that's where we are. We sort of assume that, let's do the craziest thing that we can do right now with the craziest devices and the highest amount of compute that we have available to us. And we've just gone a little bit wild there. And I think it's time for us to think about how we can develop technologies under some constraints. And that there's a lot of really interesting technical contributions to be made there too.
Good. Thanks. Now we have Anindra Saha.
Yes, thanks, Gaurav. And thanks, Peyman, for, yes. I don't know if you can hear me?
Yes, we can.
Okay, perfect. Thanks, Peyman, for that answer as well just before. That relates directly to my PhD work in embedded computer vision. So what I'm trying to do is essentially, we've got these massive models. How do we bring them down to, hardware that's available nowadays in a resource-constrained environment so that we can upscale the deployment of, computer vision technology. So that's fantastic to hear that, that's an area of interest. And also, thank you for your contribution towards the Pixel 3. I myself am a big user of that and a big beneficiary. And the one thing that sold me about this was I took a low-light photo with the Pixel 3 on one of my friend's cameras from a building 90 stories high. And looking down at the Gold Coast sort of city, you could actually read the road markings and everything 90 stories down. So that's really what impressed me so much that I ended up getting this phone. So really impressive stuff.
That warms my heart. Thank you.
Absolutely, it's awesome. So the question that I had was with regards to the way you guys were doing the super resolution with multiple frames. You mentioned that it aggregates multiple frames to deliver a single frame. What is the actual underlying FPS of the camera?
Well, for video, that's different, right? So for video, we shoot, 30 frames a second, 60 frames a second, etc.
Yeah.
But for the burst process, the number of frames per second is highly variable.
Okay.
That's in fact part of the control mechanism for the burst processing pipeline. So if, for instance, imagine if you have a scene that is dark.
Yeah.
You want each one of the shots that you take, each one of the frames that you capture to be slightly longer so that you capture a little bit more light.
Right.
And then it depends on whether your camera is stationary or handheld, and we can detect that. So if the camera is perfectly stationary, we can actually increase the exposure time, and we can increase the number of frames. So FPS doesn't have to be very high. We can take, for example, if the camera is perfectly stationary, we can have a total exposure time as much as, let's say, 4 minutes. And in that 4 minutes, we can take just 15 frames. Okay. On the other hand, if you're in a scene that's perfectly bright, well lit, but you have lots of objects moving, you might want to have a very different number of frames per second. So there's no single answer. It's highly variable, and it's dependent on the scene that you're looking at.
Okay, right. And when you are basically filling in the images with the multiple frames, sorry if I missed this before, to understand how the frames are sort of moving with respect to each other, do you use like an accelerometer or something like that to get that spatial information?
Right. So the accelerometer and the gyro that's on the device isn't accurate enough to give you information, give you enough information to align the images.
Right.
So in order to line the images up, we basically use optical flow. You know, if you're a computer vision person, you know what I'm talking about. There are many algorithms for computing optical flow, and we have to. So there's two things worth mentioning here. If you're just aligning frames together for just a regular camera mode, you can do optical flow with a single pixel accuracy, like 1 pixel accurate optical flow, and you'll get a fine image. But if you're trying to do it for zoom, and you want to do this super resolution processing, you actually need half the pixel accuracy. So you can use the same algorithm, but for instance, if you're using a multi-scale algorithm, it means you have to do optical flow at more scales of that pyramid, so you can get to a finer resolution at the fine scale. So these are sort of, some of the optical flow work is sort of classical optical flow, but we have to play a lot of tricks to make sure we get the accuracy that we need, and also to be able to do it fast enough. So remember, if you take 15 frames, you're measuring the optical flow between the base frame and 14 other frames. So it has to be done very, very fast.
Okay. And I assume then this technology is not applied to the video capture then?
The video capture uses its own technology stack, but there are certainly a number of components that are common. I'm not at liberty to go into the details of what is what, but yes, there are some parts of the process, parts of the finished pipeline and so on and so forth that are related to one another.
Okay, sure. Thank you. Just one last question I had was, in the slide where you were comparing the image resolutions of multiple cameras, one was like 35 millimeters or something like that. Was that the resolution? Was that the focal length?
No, 35 millimeter really just refers to the size of the sensor.
Okay.
When I talk about resolution, it's not just the number of pixels. It's actually a measure of optical resolution that is made in a lab. The typical units that are measured there are things like lines per millimeter. So you put a resolution chart in front of the camera at a certain distance, you take pictures, and then you crop out a part of that picture that has parallel lines right next to each other, and you literally count how many of those lines you can read.
Okay,
And that gives you an idea of, what is the resolution. There are other things you can actually physically measure, like modulation transfer function, point spread function, and so on and so forth. So the conclusions that I mentioned to you with respect to comparing our device to, for instance, Micro Four Thirds cameras, those were actually very carefully measured things in the lab.
Okay, right, sure. Fantastic. Okay. Thank you, Peyman.
Sure.
Well, next we have Bhavani. Bhavani, are you there?
Yeah.
Good.
Hi, Peyman. Thanks for the really interesting talk. So I was thinking that one of the problems in handheld devices is the amount of shake while taking the photos. And you mentioned that you can use optical flow to actually stabilize the photos. So, I mean, this is related to the previous answer that you gave, but do you think we can also use the accelerometer and the gyro information along with optical flow to stabilize it better?
Yes. So that is, in fact, sorry, go ahead.
No, that's it. So can we use the accelerometer and gyro with the optical flow?
Right. So let me kind of take you through the whole process of what are the different things that are done to align the images together. So the camera does have a gyro. It has an accelerometer, and it measures how much things are moving. That information is used to actuate what's called an optical image stabilizer. An optical image stabilizer literally takes the optics of the camera and the lens and moves them around so that you can stabilize the image at very, very coarse scale. Okay, so that sequence of images I showed you where things were moving a lot and then they were moving a little. So that first step is the optical image stabilization. Optical image stabilization will align images that are as much as several hundred pixels apart from one another. Okay, so that's step one. Then the images that are captured are still misaligned, but they are now misaligned by more like tens of pixels. Okay, that is also relatively easy to align, and we can just figure out like, okay, this image is 10 pixels up and to the left, and we can align that. Then there's more fine scale errors that are on the order of just a few pixels, maybe a couple of pixels. Then for that, we need optical flow. And in order to get sub-pixel resolution, we need multiple iterations of optical flow. So there are various steps. There's optical image stabilization, there's electronic image stabilization, there is very coarse scale optical flow, and then there's very fine scale optical flow. All of these steps have to take place so that we can have an aligned set of burst images so that we can merge them together. I hope that that clarifies.
Yeah, that clarifies it. Thank you so much.
Sure. Thank you. So we are done with the chat, questions in the chat. Does anyone have any question that they want to ask? Yeah. Okay, so I'll ask a few, I think. So how much of deep learning models are used in this sort of image processing pipeline in real time? Are there any or there none?
Yeah, that's a great question. So there are various components in the camera that are deep learning based. Actually, they're not so deep that they're for example, the color correction is learning based. As I said, the part of the upscaling is learning based. Again, a relatively lightweight model. But to kind of put your question into broader context, you might ask, why not just train one massive network and have all the raw data just kind of pumped into it and a high quality image out? Okay, that's a very reasonable question, and believe it or not, it's something that people have thought about and experimented with and so on and so forth. The problem there is that we spend an inordinate amount of time fiddling with this pipeline. We have many buttons and sliders and tuning variables and hyperparameters that we adjust. And each one of those has a relatively subtle effect on the final quality of the image. That is, at least for the time being, a rather impossible proposition with a deep model. We don't have, especially with generative models, it's very, very difficult to control at a very, very fine kind of local pixel scale what happens. Okay, so that's one problem. Tuning is extremely difficult if we just go to a deep learning model end to end. The second thing is that there's still room for improvement in deep models to try to avoid producing artifacts that are not exactly desirable in the commercial product. In generative models, there is a tendency to produce artifacts that are not precisely realistic, and we want to avoid those at all costs, especially when it comes to things like photographs of people, pets, objects that are very close to people's hearts. We don't want to generate images that are going to have the wrong emotional impact or give the wrong idea, make somebody look like somebody else. Those are absolutely things that we want to avoid doing. And so obviously, deep networks are going to play an increasingly important role over time, and they have already played a huge role in computer vision. It's just been slower for computational photography because we care so much about the pixel level details of the image as opposed to the more gross semantics of the image.
Cool, thank you. Again, one last time, I think, if anyone has any question, otherwise I'll keep asking. Okay, I'll go ahead again. Okay,
Hi,
yes, please go ahead. Yeah, Kranti.
I have a question. Thanks, Peyman, for a nice talk. You mentioned that standard cameras have large sensor size as compared to mobile cameras. But is it not counterintuitive? Like if you're having a large sensor size, then it will produce a more blurring effect in the image?
No, so it's the sensor size is, so what I'm talking about is the actual silicon die on which the pixels are sort of carved out. So the reason why a DSLR, for example, can capture, I don't know, 35, 50 megapixels is that they have a die that's maybe 10 times the area of the sensor that's inside a cell phone. And so they can have maybe 3 times as many pixels, and each of the pixels can be 3 times larger than the pixel size on a mobile device. So they can have more pixels, and they can have pixels with less noise in them. And on top of that, you have very sophisticated optics that sit in front of that sensor, so they can focus the light very, very well on the sensor. And so they have all the advantages of having a large device, low noise, and tremendous optics, very, very expensive optics. So no, the quality with an expensive device that doesn't have the limitations of a very thin mobile device, the quality can be tremendously higher.
Okay, thank you.
Sure.
I think we are almost at the end. If anyone has a last question.
I have a very related question of what we were discussing earlier. So I have came across few papers where the method is just to represent a video sequence in the form of an image, and then we can perform the operations on that image for some, let's say, video classification task or anything. So I'm just curious that if the similar concept can be applied here just to improve the image quality. Like, can you please share your thoughts on that?
Yeah, I guess I'm not sure exactly what work you're referring to. We've always, at least in my own work, I've always thought of videos as, videos are like images kind of in a cube, right? We tend to do a lot of the processing that we do in images is based on looking for self-similarity in different parts of the image. Like, for example, for denoising, if you want to denoise a part of the image, you can find similar patches around it and do that. And when you talk about videos, then that very same thought process can be applied to not just a given patch within an image, but a given patch within an image and across many, many images. And the notion of optical flow is the same. If you think about an image and let's say contour lines in an image, if you have a moving image, then those contour lines in time define basically the optical flow. So there are a lot of similarities, and I wouldn't be surprised. I mean, like I said, I'm not familiar with the specific set of papers that you're mentioning too, but there are a lot of similarities between the kinds of things that we do in video processing and the sort of things that we do in kind of burst processing. You can also imagine if you have a video sequence, right? You can apply burst processing to a moving window in that burst, right? And so, start with the first 10 frames, produce a single image out, then move 1 frame forward, produce a single image out. So you can actually use exactly the algorithm that I just showed you on a video and produce high quality images as well. So I want to confirm kind of your intuition that, yes, there are a lot of similarities between burst processing and video processing at a very high level.
Thank you.
think we are running out of time. Divya, you have raised your hand. If you have a quick question, please go ahead.
Yeah, thank you, Peyman, for the wonderful talk. I had one question regarding the electronic image stabilization. So how different is EIS from OIS? That's my question.
Right. So OIS is done purely optically by moving the actual optics, and EIS is done by actually looking at the images across time and aligning them very quickly electronically. So one is optical, and the other one is more done on the sensor side. So before we log off, let me also mention a few colleagues and I just wrote up a paper that is effectively, if you like, a summary of the talk that I just gave you. So if you're interested in reading, I'm just going to share this in the chat. I just shared the link to the archived version of the paper. This should be also appearing in the annual reviews of vision science, but in the meantime, it's available if you want to get into some more details, and there are ample citations to other works that you can also follow up on. Thank you.
Cool. Thank you, Peyman, for that. I think that will be really useful for many of us here. And this brings us to the end of the session. Thanks, Peyman, again. This was really fantastic to sort of relate to what all happens when we keep on clicking these pictures on our phones. Really fascinating, and I think encouraging for budding researchers to maybe pursue some of these directions as their, as part of their research career. Thank you so much for accepting the invite and giving this wonderful talk.